In this video on integration, these are the topics that will be covered, and they're going to appear in no particular order. We're going to be using inverse trigonometric functions, use substitution, completing the square, then employing inverse trig functions, long division, and separating into multiple fractions. This video is about identifying integrals that have solutions that contain inverse trigonometric functions. So there's two parts to this. First of all, it's identifying which of the inverse trigonometric functions that you see here in the solutions that you're going to use with which particular pattern in the integral. And the second aspect is identifying or memorizing the formula of the solution itself, because as you see, they differ slightly. So we're going to do this video in two parts. First, I want to point out that we only have to memorize inverse sine, otherwise known as arc sine, inverse tangent, and inverse secant. And that's because the formulas for the inverses of their cofunction differ only by a minus sign. So what would happen is you'll have a minus sign in the original integral, you'll pull that out in front, and that'll leave you with one of these three, which limits the number of formulas we have to memorize. Okay, so what I'm going to do is I'm going to move part of this off the screen, and then we're going to come back and I'm going to show you how to look for certain patterns in this integral to determine whether we're going to use inverse sine, tangent, or inverse. Okay, as mentioned, the first part is identifying which of these three is going to go with which of these patterns. So I have these listed in alphabetical order, and I want to show you how I memorize what goes with what. Okay, look at this one in the middle here. This one in the middle is the only one without a radical sign in the denominator. So in other words, if I just dot this in, you could see that this particular pattern does not have that coverage. So the way I think of that is an awning or an umbrella that protects us from the sun. So if you envision these other functions here have this umbrella, have this awning protecting this term or this integral from the sun, this one doesn't have it. This one is going to get tanned. All right, so I think you know where I'm going. This is going to be the inverse tangent function with no umbrella to cover it from the sun. Now, the second thing I want you to notice is, as we know, the sun, as we know from biology class, the sun has ionizing radiation properties, and those radiation properties can change the genetics, for example, and cause cancer by altering DNA. So look what's happened. This one, the tangent, inverse tangent function, is the only one with a positive sign. So the way I think of it is the default, the baseline is a negative, but because of that ionizing radiation, this is changed to a positive. Okay, so now we know who tangent, inverse tangent is. Let's look at the other two. Now, folks, don't forget, the A stands for a constant, the U stands for a function. So for example, you're going to have the square root of 9 minus 4x squared in the integral. This would be the A because it's a constant. So this would pattern to a squared being 9 and eventually a being 3. This u is a function. That's u squared. And eventually we'll take the square root of that and you're going to have 2x equaling your u. So look at this. The remaining two functions, okay, we know one of them is going to be sine and one of them is going to be secant. The remaining two functions, the default, the usual, is to have the a first. All right, we see that here and we see it in the tangent. But all of a sudden, down here, we have the u function first. And then for emphasis, we see it again. So this emphasizing the u, First, by putting it in front, and second, by putting another version of it in front of the radical. That's your secant right there. Okay. Finally, by definition, this is going to be our sine function. And the way I think of this is simple Simon. So simple Simon basically has the default choices. It's got a first, and it's got a minus sign, and it's got a radical. Simple Simon. That's the way you memorize, or I memorize, which inverse trigonometric function goes with which pattern. So now I'm going to move this over, and we're going to talk about how to memorize the actual solutions and match them to the inverse trigonometric functions themselves. Let's now talk about how to memorize the formulas of the solutions. Let's start with simple Simon. We can see he's so simple. First of all, let me mention that all of these here in the argument of the inverse trigonometric functions, they all have u over a. All right, now simple Simon has nothing out front. Let's now move to tangent. Tangent has an a, 1 over a here. Match it with that a right there and that a right there. Just memorize a, and a. Finally, you have arc secant, or inverse secant. Remember, here's the guy who puts u first for emphasis. Secant likes to have the umbrella brought back in for sun coverage. So therefore, think about this absolute value sign in the numerator only for the inverse secant as restoring sun coverage for this exposed u right there, making up for the fact that that u is getting sun exposed. Here we protect it with inverse secant. Folks, throughout this video we are going to be working on the following 4 integrals as well as some others, and I want you to notice something. Let's look at this first one. We have dx on top. The formulas had the dx's here with this as a 1. Okay, so this first one, look, there's no radical sign. There's no sun coverage for that denominator. This denominator is getting tanned. Not only that, the ionizing radiation has changed the default negative sign to a positive. This solution is going to involve the inverse tangent function. Down here, we have the return of our sun coverage. But notice, this is a function of x. That's our u squared. This is a squared. And it has a version of u for emphasis in front. This is our inverse secant function in play. Finally, down here, we have our default minus sign. We have our sun coverage. We have our a squared first. That is the sine function known as simple Simon. Now, very important, folks. I want you to draw your attention to this integral up here. Now, I'm hoping I can execute this removal here. Okay, so far so good. And then I want to make this a little bigger so you can see the integral. Okay, not too bad. Okay, so now what I want to do is I want to emphasize that this integral is going to get split up into 2 integrals. And the first part here has an x on top, right here, but the second integral does not. This first integral, we are not going to have an inverse trigonometric function involved. It's okay to have the x in the denominator, but if you have the x in the numerator like that, we're going to use routine u substitution. All right, routine u substitution. We're not going to end up using inverse trig. Here, however, because that's a dx on top, or if you think of it this way, we have a dx out here with a 1 on top. This answer will involve an inverse trig function. In our first example, as we approach this integral, we recognize that there is no x function in the numerator. So this is similar to what we saw on our formula list, having 1 over a radical. This to me looks like an a squared. This looks like a u squared. We have the default minus, and we have a radical. This means that inverse sine might be an option to solve this integral. We're going to let a squared equal 4. We're going to let u squared equal x squared. We're going to take the square root of both sides. We're going to get a equals 2 and u equals x. Next, we're going to rebuild our radical so that, rebuild our integral so our radical looks like, excuse me, a squared minus u squared times dx. Okay, we're going to come over here with the du, and we're going to take the derivative of both sides, and we're going to get du equals dx. We're going to replace dx with du, so we're going to have the integral as shown with du. This is inverse sine. Now for the solution, recall that inverse sine is simple. All it has is the u over a plus c. There's no fraction out in front. So we're just going to replace the u and the a accordingly. So our u equals x, our a equals 2, and that is our final indefinite integral. Next, we have an integral that we're suspicious we might be able to use inverse trig as a solution. If we place the dx out here, we're left with a 1 up top. We notice that there is no radical. Also, that's a positive sign. That means lots of sun exposure. That negative sign, which is the default, turns to a positive. We're talking about inverse tan function. Okay, so we're going to let, excuse me, a squared equal 2 and u squared equal 3x. That means a is going to equal the square root of 2 and this should be 9x squared, and u is going to equal 3x. All right, we're going to go ahead and rebuild our integral. We're going to have 1 over square root of 2 squared plus 3x squared. This is none other than a squared plus u squared. And then here we're going to take du and take the derivative. If u equals 3x, then du is going to equal 3 times dx. So we're going to replace dx with du divided by 3. So what was dx is going to be removed. We're going to take du over 3, and then we're going to bring the 1/3 out in front, and this is going to be our integral. We're going to recognize that since we have an a squared and a u squared, this is inverse tangent. That is going to be in our solution. Let me rewrite it over here in light blue. So we're going to have inverse tangent involved. Recall, inverse tangent has 1 over a out front and u over a in the argument. So in the end analysis, this is going to be 1 over the square root of 2 inverse tangent of u, which is 3x, over a square root of 2, but we can't forget the 1/3. So we'll leave it up to you and your teacher if you want to simplify that fraction any further, but this along with the plus c is the answer to this integral. Folks, before we leave that last example, I want to point something out about the inverse tangent being used in the integration. Notice the example that you were given that we just did a few moments ago did have the u squared second, and that's what we're used to seeing. The formula that we're looking for when we're going to employ inverse tangent is a squared in front. However, if for whatever reason you're presented the integral like this, where it appears that the u squared is in front of the a squared, that's okay because we're dealing with addition. So you could very simply reverse these and do the integral as we did a few moments ago. In our next example, we have 1 in the numerator, and we do have an x, but it's in the denominator. So the fact that that x is out front, we still have a radical, we still have a minus sign, we are suspicious that this is going to be inverse secant playing a role. Also, inverse secant, recall, has the u squared first and the u or portions of u out in front for emphasis. Okay, so with that in mind, let's go ahead and let u squared equal 4x squared and a squared equal 9. That means u is going to equal 2x and a is going to equal 3. We're going to come down here and we're going to do du is going to give us 2 times dx, and dx is going to be du over 2. We're going to rewrite this integral. We're going to have fraction 1. Instead of dx, we're going to replace that with du over 2. So this was dx. Then we're going to have x times the radical of u squared minus a squared. So there's no x here to cancel out that x, so we're going to have to solve for x in this particular case. So recall, here in pink we have u is equal to 2x. We're going to solve for x and we're going to get u over 2. So I'm going to remove that x and replace that with u over 2. Okay, like so. All right, now as we simplify this u over 2, we're going to be very careful. Let me erase this and get some room. Okay. All right, first thing we're going to do is bring this 1/2 out front. So we're going to have 1/2 the integral, and we're going to have du over here. Now, if we look at this denominator here, this has u up top, it has the radical up top, u squared minus a squared, and it has a 2 beneath with a 1 on top. So the way I'm going to handle this is I'm going to simply multiply top and bottom by 2. That's going to result in this canceling out with a 2 up top, and then I'm going to bring that 2 out front. These are going to cancel, and we're going to be left with this final integral, which is very inverse secant friendly, times du. Okay, building our answer, building our solution to this, we're going to have the following formula for secant. Inverse, we're going to have that's 1 over a, inverse secant u over a, but recall that u gets extra sun protection with an absolute value sign. Okay, so we're going to fill it in. A was 3. We're going to have the absolute value of u, and we know that u equals 2x, and this is our final solution. In our next example, we see a construct in the denominator that leads us to think that inverse trigonometric functions are going to be used in this integral. However, this numerator is not what we're used to seeing. We're used to seeing a 1 up here, or a constant that we bring out. But fortunately, in this integral, we're given 2 terms in the numerator, and that is an invitation. That is a license to split this up into 2 integrals. All right, we're going to see that's a very powerful maneuver. And later on in this video, we're going to see that we create additional terms in the numerator in order to be able to do this. We're literally going to do things like add 6 and subtract 6 so that we create enough terms to separate the integral. So here, we don't have to do that latter approach, but we can go ahead and create two different integrals. So we're going to have x over 4 minus x squared dx plus the integral of just the 2 over the square root of 4 minus x squared dx. Okay, looking at this first integral, we see the construct again in the denominator. However, we see the x in the numerator that we're not used to seeing when we use this technique. We're used to seeing a 1 here, or the dx in the numerator. So here we're going to use routine u substitution. We're going to let u equal 4 minus x squared, as we often do. We often let u equal what's within a function. When we take our du, we're going to get negative 2x dx, and our dx is going to equal du divided by negative 2x. As we rebuild this radical, we're going to have x in the numerator over the square root of u. This dx is going to be replaced by du over minus 2x. Okay, that used to be dx. We're going to cross out these x's, and we're going to have the integral of du with a negative 1/2 out front of the square root of u. We're going to change this to negative 1/2 times the integral of u to the negative 1/2 du. We're going to add 1 to the exponent and then divide by the new exponent. So we're going to have u to the 1/2 divided by 1/2. Dividing it by the new exponent is the same thing as multiplying by its reciprocal, and that's going to result in these two canceling out. So our end result is going to be negative u to the 1/2 plus c. We're going to replace our u with the 4 minus x squared, and we're going to reinstitute the radical sign instead of that fractional exponent, and this is going to be the first part of our integral. Now that we have the first part of the integral done, let's go ahead and focus on the second part of the integral. So here we have a constant up top. Therefore, this is going to be more amenable to using inverse trig functions. We have the default minus, we have an a squared out front, a u squared second, and to me this looks like inverse sine because we do have sun coverage. Okay, so we're going to let a squared equal 4, we're going to let x squared equal x squared, a is going to equal 2, our x, I'm sorry, not x squared, this should be u, sorry. Our u is then going to equal x. We're going to take our du, and that's simply going to be dx. We're going to rewrite our integral by pulling the 2 out front. We're going to have a 1 on top. Instead of dx, we're going to replace that with du. And down below, we're going to have a squared minus u squared. We're then going to build our solution. We're going to have our 2 out front. Here's our inverse sine. We're going to have u over a, and that's it. The sine function solution is very simple. So we're going to have 2 times inverse sine. Now we're going to bring our u value, which we know is x, our a value, which we know is 2, and this, folks, is going to be our final answer. We're going to combine these two with a plus sign in between. Next we have this indefinite integral, and we see that there's a 1 on top, and we're hoping we might be able to use inverse trigonometric functions, but it doesn't look like it's amenable to it. So in this case, we are going to complete the square and create some perfect squares in the denominator. So recall, to complete the square, I think of it more as creating the square. We're going to separate this plus 7 out a little bit, give ourselves some room. And the way I do it is, you have two numbers. You have a drop-down number, which is going to come down into this parentheses and be squared, and then you have a makeup number, or an add-on number over here, or a compensating number here. So I'm going to take 1/2 of this, middle term, we're going to get -2. That's our drop-down number right there. And then we're going to square this to get our add-on number. And when we do that, this is separated from the +7. And we have to go ahead and compensate for that +4 by doing a -4 here. So folks, that yields x minus 2 squared plus 3. So with that in our denominator, we're thinking about inverse tangent. So we're going to don't forget, with inverse tangent, you have plus here, so you can swap these. So here, we're going to have 3 plus x minus 2 squared if we reverse the order. So we're going to let a squared equal 3, and we're going to let u squared equal x minus 2 squared. Therefore, a is going to equal the square root of 3, and u is going to equal x minus 2. We're now going to rebuild our integral, and we're going to have 1 times dx. We're going to have a squared plus u squared. And the resulting trigonometric solution is going to be 1 over a inverse tangent of u over a plus c. So when we substitute down here in light blue, we're going to have 1 over the square root of 3 inverse tangent of u, which is x minus 2, over the square root of 3 plus c. Next, we are presented with this problem where we want to find the area bounded by the graph of f of x listed here and the x-axis. And these lines, x equals 3/2 and x equals 9/4. So basically, we have some function here, and we don't know what it looks like. Let's say it looks like that. And we're trying to find the area between x equals 3/2 and x equals 9/4. So we have to take the definite integral and compute the area. Okay, so we're going to take the integral from x equals 3/2 to x equals 9/4 of 1 over the square root of 3x minus x squared dx. Now, there's a 1 here, so we're suspicious we might be able to use trigonometric functions. But we really don't have it set up here. If here we have x with both terms, so we can't really establish an a term, which would be a constant, and a u term, which would contain x. So based on the last problem, we're going to consider completing the square here. Now, with that negative, it makes things a little difficult. So let's try to do this. Let's pull out the negative, and that's going to give us x squared minus 3x, like so. Yes, I always redistribute the negative. So we're going to get negative x squared plus 3x, negative x squared plus 3x. Okay, so let's complete the square here. And we're going to have a drop-down number here, which would be, we're going to have an x. We're going to drop down minus 3/2, like so, squared. And then we're going to add 9/4 here. And as a result, we're going to compensate by subtracting 9/4. But we got to be very careful here because we didn't add a 9/4, we added a negative 9/4. So we compensate by adding a 9/4. Again, that negative means we added a negative 9/4 to the situation, plus 9/4 neutralizes that. So now we have this going on. We have 1 over the square root of x minus 3/2 squared plus 9/4 with a negative here. So we're going to rearrange these, and that's going to yield 1 over the square root of 9/4 minus x minus 3/2 squared. And this fits nicely because we're going to let a squared equal 9 over 4, a equals 3 halves, and then we're going to let x minus 3 halves squared equal u squared, which means x minus 3 halves is going to equal u. So now, folks, if we rewrite this integral, we now have the integral from 3 over 2 to 9 over 4 of 1 over the square root of a squared minus u squared. And that is going to be the inverse sine graph. So let's go ahead and make some room. All right, our solution is going to be inverse sine of u over a. So our u is going to be 3 halves, x minus 3 halves. That's our u. And our a value is going to be 3 halves, like so. Okay, and we're going to evaluate this inverse trigonometric function from 3 halves to 9 fourths. Okay, let's clean up and come back and do that. Continuing on with the evaluation, we have this set up here. We remind ourselves that inverse sine, the domain, is located from negative pi over 2 to pi over 2. So first we're going to plug in 9 fourths here. So we're going to have inverse sine of 9 fourths minus 6 fourths over 3 halves. And that's going to be subtracted. We're going to then subtract inverse sine of 3 halves minus 3 halves over 3 halves. So here on the left, we're going to get inverse sine of 3 fourths over 3 halves. And one quick way to simplify that is it's going to be 0.75 over 1.5, or just 1 half. And this is, of course, is going to go to 0. So here in white, we're going to have inverse sine of 1 half minus inverse sine of 0. So when we look at inverse sine of 1 half, we ask ourselves which angle in that domain listed above has a y value of 1 half. So the way I like to do these is short, medium, and long. So right there, that's a short distance for the sine. That's going to be 1 half. This is square root of 3 over 2. And this distance is 30 degrees, or I should say that input angle is 30 degrees, otherwise known as pi over 6. For inverse sine of 0 within this domain, it's going to be 0 degrees. Therefore, our final area is going to be pi over 6. Let's look at this collection of 4 indefinite integrals and talk about strategies, how to approach each one. So you see here for the first one, we have x squared plus 4 quantity squared. Folks, terms are our friends. So what we can do is go ahead and just FOIL that out. That would give us the integral of x to the 4th plus 8x squared plus 16. And then we could just break this up into different integrals. So the first indefinite integral would be x to the 5th over 5. And then we're just basically adding and dividing by the new and improved exponent, plus 16x plus c. So it's so much easier if we could separate things into terms. Here we're going to do the same thing. This is the same problem, and then all we're going to do is go ahead and distribute that x squared. We're going to have slightly larger exponents, but we're going to do the same thing. Same here. We're going to distribute that x, create a bunch of terms. But folks, here we're in a pickle, because unless we're prepared to use Pascal's triangle, we're not going to go ahead and develop this to the 12th power. So here, when we see this, we have to change gears a little bit, and we're going to use u substitution. We often use u to equal something in parentheses. We also use it for something in an exponent, in a denominator. So here, we're going to let u equal x squared plus 4. du is going to equal 2x times dx, and we're going to solve for dx. We're going to have du over 2x equals dx. We're then going to go ahead and rewrite our integral. So now we're going to have x times u to the 12th power, and dx is going to be replaced by du over 2x. So that was 2x. That was dx. Okay, these x's are going to cancel, and then we're going to pull out the 1/2, and we're going to end up with 1/2 times the integral of u to the 12th power du. We're going to add 1 to that exponent, make it u to the 13th, and we're going to divide by the new and improved exponent, and we're going to have a final indefinite integral of 1 over 26 u to the 13th plus c, and then we're going to go ahead and replace u with the x squared plus 4 to the 13th times 1 over 26 plus c, and I don't know if you could see that, that is your final answer. This next array of indefinite integrals features 3 that we're going to use one technique, and a 4th that we're going to use a different technique. And let's take a look at each of these. So here we see the square root construct, and we're hoping we might be able to use an inverse trigonometric function, but we see an x in the numerator, and this number is not very high. So let's reserve judgment on that one. Here, this looks like a classic inverse sign, where we're going to have a squared in front. We're going to let a squared equal 4 and let u squared equal x squared. A is going to equal 2 and u is going to equal x. So that would utilize inverse sign. Same thing here. Here we're going to have a squared equal to 1 and u squared equal to 4x squared. A is going to equal 1 and u will be 2x. And the important thing is that there's a 1 on top. And when you have that scenario, that is amenable to inverse trig. And this is also going to be inverse sign. Now here we do have an x in the numerator, but look how big that exponent is. And often when you have that large exponent and then you take the derivative of it, you have enough x's lying around to cancel out the denominator. So let's see where that takes us. So if this was going to be a squared minus u squared, we're going to let a squared equal 4 and a equal 2, and then we're going to have u squared equals x to the 8th, u equals x to the 4th. So then if we took du, we would have 4x to the 3rd times dx, and if we solve for dx here, we would have du over 4x cubed, and lo and behold, those x cubed would cancel out, and we'd bring the 1/4 out front, and we would use inverse sign. Now this one, that exponent is small, and if we tried to do the same thing, it would not work out, because our a value, a squared, is going to equal 4. Our u squared would equal x cubed. And this is an ugly perfect square anyway. So in this scenario, what makes this different is we're going to use u substitution. So oftentimes the u is under the function. Here it would be the square root function. So we're going to let u equal 4 minus x cubed. The other thing that's inviting about this technique is that you see the derivative right in the problem up there in the numerator. So we're going to let du equal negative 3x squared dx. We're going to solve for dx, and we're going to rewrite the integral as x squared over the square root of u times, and now we're going to rewrite dx as du over negative 3x squared. When we have that, the x squareds cancel out. We're going to pull the negative out front, and we're going to bring we're going to pull a negative 1/3 out front, and then we're going to bring the u up, the exponent up top, and we're going to just do a standard integration without involving trigonometric functions. Finishing up that integral we were just working on, we're going to let u equal 4 minus x cubed, that should be, and we took du, we solve for dx, and then we rewrite the integral. These x squareds cancel out. We're going to pull out the negative 1/3, and we're going to have du over u to the 1/2. We're going to bring that up top. Integral of u to the negative 1/2 du with negative 1/3 out front. Okay, we're going to take this, we're going to add 1 to the exponent, and that'll make it 1/2, and we're going to divide by the new exponent 1/2, which is the same thing as multiplying by its reciprocal. So we're going to have negative 2/3 the square root of u, which is 4 minus x cubed, plus c. Next we have this indefinite integral cotangent of x. We're going to change this to cosine x over sine of x, and we're thinking u substitution because we see the derivative of the denominator right there. So we're going to let u equal sine of x, and du is going to be cos x dx. We're going to solve for dx and get du over cos x. We're going to go ahead and substitute. Instead of dx, we're going to have du over cos x. These are going to cancel, and you're going to end up with natural log absolute value of u plus c, and then we're going to go ahead and replace u with sine of x. Next we see an x squared plus 8 in the denominator with a plus sign. We're thinking maybe this could be inverse tangent, but our x is in the numerator, and this exponent is not very big, so we're going to end up just using u substitution here. We're going to let u equal the denominator, as we often do. We're going to take the derivative of that. It's going to be 2x dx, and we're going to have du over 2x equaling dx. We're now going to substitute that into our integral. We're going to have x over the u times du over 2x. The x's are going to cancel out. We're going to pull out the 1/2, and we're going to have du over u. We're going to end up with 1/2 ln absolute value of u plus c, 1/2 ln of absolute value of x squared plus 8 plus c, and truly we really don't need those absolute value signs because x squared plus 8 will be a positive argument. Next, we might be tempted to use a trigonometric inverse function here, but here we have the u in front, and we have a plus sign under a radical. Nothing really fits despite the fact that we have 1 in the numerator. So let's let u equal x plus 8. We often let u equal something that's within a function or up in an exponent, etc. Our du is going to equal dx. So we're going to have 1 over the square root of u times du. This is going to be the integral of u to the negative 1/2 du. We are then going to add, to do our antiderivative, we're going to add 1, which is going to add 2 over 2 to make this 1/2. We're going to divide by our new exponent, which is 1/2, and that's the same as multiplying by its inverse, which is 2, or I should say reciprocal, which is 2. So we're going to end up with 2 times the square root of x plus 8 plus c. Next we have this integral, not really amenable to inverse trig. We're going to use u substitution for this in the parentheses. Let's let u equals square root of x plus 8. Be very careful not to extend that radical to include the plus 8. Okay, so for du, we're going to have 1/2 x to the negative 1/2, and then we're going to bring that down into the denominator. So we're going to have 1 with 2 on the bottom and the square root of x down below times dx. When we solve for dx, we're going to multiply both sides by 2 square root of x. Du will be our dx. Okay, we're going to go ahead and substitute that in for dx. That's going to yield the integral of 1 over square root of x times u times our dx, which is going to be 2 radical x du. The square root of x's are going to cancel out. We're going to pull out a 2, and we're going to have the integral of 1 over u du. Okay, moving over here, I know this is getting messy, my apologies. We are going to erase everything except the u. I want to know what that is. And we're going to end up with 2 natural log absolute value of u plus c, 2 natural log of the square root of x plus 8 plus c. In this integral, the first thing we notice is that there's 2 terms on top and only 1 term in the denominator. This allows us to split these 2 fractions. And we know what to do with this integral. This will just become x plus 4 over x, and this is x squared over 2, and this is going to be the integral for 1 over x, and we're going to use the ln of x property here. Okay, but there's another way to do this. If this doesn't jump out at you, you can use long division here. And of course, when you use long division, you have to have a higher degree on the top than on the bottom. So we'll put the dividend inside the shoebox and leave the divisor outside. And when we do our long division, we're going to get 0, we'll bring down the 4, and we're going to have 4 over x as our remainder. So this integral becomes x plus 4 over x, which is the same integral as when we split the fraction. This next integral can be done in one of 2 ways. The first thing we can do is use u substitution. As we often do, we let u equal the denominator. The du is going to be 1 dx, so dx is going to equal du. So when we rebuild the integral, we have x over u times du. So because that x does not cancel out, we have to solve for x. So x is going to equal u minus 4. So when we rebuild the integral again, we have u minus 4 over u. And folks, look what we have. We have 2 terms in the numerator and only 1 in the denominator. So we could split this integral into the integral of these 2 entities. Okay, so that's this over the denominator minus that over the denominator. And when we do that, we can change this to the integral of 1 and pull out a 4 like so. So the integral of 1 is just going to be u, and the integral of minus 4 times 1 over u is going to be minus 4 ln absolute value of u plus c. And with u, we're going to replace that with x plus 4 minus 4 ln absolute value of u plus c. But folks, we can go ahead and combine the plus 4 and the plus c, and we can write it like so. Absolute value of u plus c2. I might add a little 2 there just to show that I made a change with the plus 4 and the plus c. The second way to do that same integral is to recognize that we could still do long division even though the degree of the numerator is the same as the degree of the denominator. So in this case, we're going to do 1, and that's going to yield x plus 4. And when we subtract, we're going to have negative 4. So our remainder is going to be negative 4 over the divisor. So now we're integrating 1 minus 4 over x plus 4, and that is exactly what we ended up with previously. You're going to have the integral of 1 over 4x plus 4 plus c. And when we do the integral, we're going to have x minus 4 ln absolute value of x plus 4 plus c. So that eliminates the extra step because of the substitution that we had to do for x in the previous integral. And we notice that we have u squared plus a squared in the denominator. And here it doesn't matter if the u squared is before the a squared because that's addition and we could switch these. But the problem with using inverse tangent in this antiderivative is that x. If there's an x in the numerator, it makes the inverse trig functions less useful unless that exponent is large, say x to the 4th, because then when you do the chain rule, you're going to have extra x's lying around. So in this case, we're going to use u substitution. We're going to let u equal the denominator, which is x squared plus 4. du is going to equal 2x dx, and our dx is going to equal 2x, our dx is going to equal du over 2x. So rewriting this integral, we're going to have x over u times du over 2x. This used to be dx. That allows us to cancel out these x's and pull out the 1/2, and we're left with 1/2 the integral of du over u, and this is going to end up being 1/2 natural log absolute value of u, and then we'll go ahead and substitute x squared plus 4 for u, and we have our antiderivative. With this next integral, we see that we have a top-heavy rational function, and that is amenable to long division. We cannot split this up into two fractions because there's only one term in the numerator. So let's go ahead and do long division. We're going to put x squared plus 0x in the shoebox, and we're going to have x up top. Sorry, let me clean that up a little bit. We're going to have x on top. That's going to give us x squared plus 4x. We're going to subtract, and we're going to get negative 4x. Then we're going to do a second round. We're going to get negative 4x minus 16. We're going to subtract, and that goes to 0. That goes to plus 16. And we're going to put 16 with the divisor in the denominator as our remainder. Okay, folks, then we're simply going to integrate these three terms. So our first term is going to be x squared over 2. Then we're going to have minus 4x. Then we're going to have 16 ln absolute value of x plus 4 plus c. In our next integral, we see perfect squares in the denominator, and there's no radical sign. That's a plus, so we're thinking this might be inverse tangent. We see that x in the numerator, which often dissuades us from using inverse trigonometric functions, but there's a large exponent. So let's see if that works out. We're going to let a squared equals 16. We're going to let u squared equal x to the fourth. A equals 4, u equals x squared. So we're going to rebuild this. Let's do our du is going to be 2x times dx, and our dx is going to equal du divided by 2x. So as we rebuild our integral, we're going to have a squared x over a squared plus u squared times du over 2 times x. That was dx. Okay, we're going to cross out these x's. We're going to pull out the 1/2. And this now fits the inverse tangent paradigm. Okay, our solution for inverse tangent, recall, is 1 over a inverse tangent u over a. So we're going to have 1/2, the original 1/2, times 1 over a, which is 4, inverse tangent of u, which is x squared, over a, which is 4, plus c, and then this part becomes 1/8, and the rest stays the same. Next, we see perfect squares in the denominator with a plus sign, no radical. We're thinking inverse tangent, but that x in the numerator without a large exponent pushes us towards using u substitution. Our du is going to equal 2x times dx, and our dx is then going to be du divided by 2x. We're going to rebuild the integral as x over u times du over 2x. That was our dx. The x's cancel. We're going to pull out the 1/2, and we're going to have ln of u, which is ln absolute value of x squared 16. Next, we have 1 in the numerator, so it would be nice if this was a set of perfect squares. We have a polynomial, so that's an invitation to do creating the square, otherwise known as completing the square. So first, we're going to pull out that plus 32 and give us a little room. We're going to have x squared plus 8x. We're going to have a drop-down number, which is half of the middle term, so that drops down into there, and then we have a makeup number, which is that squared. We keep these separate, and then we compensate by subtracting the makeup number there. That gives us 1 over x plus 4 squared, and this evaluates to plus 16. Okay, we now have two perfect squares. This is our u squared. U squared is going to equal x plus 4 squared. Our u is going to equal x plus 4, and our du is going to equal dx. Here, this is going to be our a squared. A squared equals 16. A is going to equal 4. We can now rebuild our integral here down in orange. We're going to have 1 over u squared, 1 over a squared plus u squared, and the du replaces the dx. Therefore, we're going to have 1 over a, which is 4, inverse tangent of u over a. U is x plus 4 over 4 plus c. This next integral is very interesting. So we have a 1 on the top, and we have a perfect square here, but x doesn't strike you as a perfect square unless you recognize that if you let u squared equal x, then u could equal the square root of x. We're going to let a squared equal 16, which means a equals 4. So now, before I forget, we're going to do du over here. So du is going to equal 1/2 x to the negative 1/2, which is 1/2 times 1 over the square root of x, which equals 1 over 2 square root of x dx. Therefore, when we solve for dx, we're going to multiply both sides by 2 radical x. And finally, our dx is going to equal 2 times square root of x times du. Okay, so what led me to continue with trying to use inverse trig functions is the fact that the x was in the denominator. Okay, so let's go back and rebuild our integral. We're going to have 1 over the square root of x times a squared plus u squared times what used to be dx, which is 2 radical x du. That used to be dx right there, was dx. Okay, now the square root of x's are going to cancel out. We're going to pull out a 2, and we're going to have our normal inverse tangent function, which is going to be 1 over a inverse tangent of u over a, which is the square root of x over 4, plus c, and then this will simply change to 1/2 out front. So here is your final answer with this simplified to 1/2 out front.